Suppose we shoot a projectile horizontally from some initial height. I hope it makes sense to you that the faster we shoot this projectile, the farther it's going to travel horizontally before hitting the floor. And this means that in principle, we can use that horizontal range to measure the muzzle velocity of our projectile launcher. So that's the main goal of this video. We want to find a formula that takes us from the measured distances here, that's the range and the initial height, back to the muzzle velocity when the projectile was first launched. So let's just move this guy over to the left real quick. And like any projectile motion problem, we're going to split the analysis into horizontal and vertical components. So there's our general horizontal equation for a projectile flight. It says x equals x naught plus v naught xt. Note there's no acceleration term there because the x acceleration is 0, provided drag is negligible. And there's our typical vertical analysis. We have y equals y naught plus v naught yt minus 1/2 gt squared. This equation does have an acceleration component to it. We've plugged in an acceleration with a magnitude of little g pointing in the downward direction, and that's why there's a minus sign out in front. So as we're plugging in values into these equations, I want to point out that I've clearly labeled the origin in this diagram. It's at the floor level. So y is 0 at the level of the floor, and our origin is directly under the release point of the projectile when it comes out of the launcher. So our initial x-coordinate is also 0. So we start working on this horizontal equation, and we can plug in a final x-coordinate of r, and that's called the range of the projectile. Again, the initial x-coordinate is 0 just because that's where we placed our origin. And the initial x velocity is just equal to the muzzle velocity of this projectile launcher because it's a perfectly horizontal launch. So plugging that stuff in, our equation simplifies to r equals v naught t. Now it's going to be useful to solve this for t, in other words, the flight time of the projectile. So we arrive at t equals r over v naught, and that guy will be useful in just a minute. Now moving on to the vertical analysis, the final y value is 0 because we placed our origin at the level of the floor. The initial y value is h, that's the height of the projectile immediately upon being launched out of the tip of that launcher. Our initial y velocity is going to be 0, so that entire term dies, and this is because it's a horizontal launch. There's no vertical component to that initial y velocity. And then of course we'll take our acceleration term to the next step. So plugging in the initial and final y values and the fact that the initial y velocity is 0, our equation simplifies to this. So it's just 0 equals h minus 1/2 gt squared. So where we're going to go from here is we're going to take our equation for the flight time from the horizontal analysis, and then we'll just sub that in for t in the vertical analysis. This should give us an equation where the only unknown is v naught, and of course that's what we're trying to solve for here. So simply replacing t with r over v naught, we arrive at this equation, 0 equals h minus 1/2 g times the quantity r over v naught all squared. So remember, we're trying to solve for v naught here. And what I'm going to do is move this entire term to the left-hand side of the equation and get rid of that minus sign. And while I'm doing that, I'm going to go ahead and apply that exponent of 2 to the numerator and denominator of that fraction. So that fraction will be rewritten as r squared over v naught squared. So we arrive at 1/2 g times r squared over v naught squared is equal to h. And now I'm going to multiply both sides by v naught squared to get that v naught squared term over there on the right. At the same time, I'll divide by h to isolate the v naught squared. So the last thing I did there is just combine all of those factors on the left-hand side into a single fraction. And what we get is gr squared over 2h is equal to v naught squared. Now all we have to do to solve for v naught is square root both sides. And I'm going to rewrite v naught on the left-hand side since we finally solved for it. Note that when I take the square root, there's an r squared inside of it, which can be pulled out as a single factor of r. And so we arrive at a formula for the muzzle velocity v naught, written in terms of all the things we can measure. And that's v equals r times the square root of g over 2h. So we have the range r and the height h. And then g, we would normally just look up an accepted value for that. And so now we're effectively using range as a speedometer for our projectile launcher. And this is a really practical process in the lab. All we have to do is put down some carbon paper at the impact point and carefully measure the height and the range, usually averaging over 10 or 20 shots, and then we can find the muzzle velocity. Now, as it turns out, the not so simple part of this process is the error analysis. It turns out that the uncertainty in muzzle velocity is completely dominated by the uncertainty in launch angle, but we haven't included launch angle as a variable in our formula. So in the next video, we're going to generalize our result to work for a general launch angle of theta, and that's going to allow us to do a proper error analysis when we get to the lab. I'll post a link to that video at the upper left when it's done, and I'll see you there.